timing. Okay. So I'm going to talk about higher order symmetries today. I don't have a question yet, a problem yet. So I'm just going to share with you what. Oh, this really is very bad. I'm just going to share with you what I've learned in the past 2 or 3 months. So in one line, what this is about is we have higher order symmetries associated with topological operators. And this powerful idea is used in many areas of theoretical physics. One of the most prominent examples is Wilson loops. So these are line operators, and I hope to get to explaining what these are at the end of my talk. So these things are applied in many areas of theoretical physics. First of all, in condensed matter physics, we have topologically ordered phases, and these characterize anionic excitations. And in QFT and gauge theory, Wilson loops are order parameters. And these are used for confinement and deconfinement transitions in gauge theory. And finally, one last example is that in string theory, Wilson loops appear in ADS-CFT. Now, to learn about this, it's best to start from the basics. And so I'll give you a quick review of our standard symmetries that we learned in symmetries in particles and fields. So before I even start on symmetries, let's talk about Hamilton's principle of least action. So given a Lagrangian, we say that Hamilton's principle insists that if you have an extremized action, then this corresponds to having some field that minimizes this extremal action. And in the case of, and when you have this, then your first order variation goes to 0. So notice that this has nothing to do with symmetries yet. Now, this gives us the equation of motion we should be using later. Now, at this point, on a completely unrelated note, we have the Noether theorem. Now, this Noether theorem states that if you have an action and a Lagrangian, then there exist certain transformations that send this first order action to 0, even if you do not have extremal action, right? So at this point, this is completely unrelated Hamilton's principle. So in equations, now in order to generalize later, I want to point out something here, which is that this epsilon parameter is a constant across space-time, and this is supposed to be infinitesimal. Now, this is a finite, possibly finite transformation, and it restricts the form of the transformation in the fields. Now, if we have a symmetry which satisfies this, and at the same time we have an extremal action, then we can impose the equation of motion, right? And it's only when you impose the equation of motions do you get the continuity equations. This should be familiar so far, right? And so this we call this the conserved currents. And we also have conserved charges. Where you integrate one of the time component along space, over all space. Now, since we are asked to draw some pictures, I'm going to draw some pictures which helps to generalize this idea. So what the conserved charge is, let's say we are in two dimensions of space and one dimension of time. Then basically your integral goes over a time slice, right? And we can think of this as we have a three-dimensional manifold M, and this is some there is d. Let's say M is d-dimensional. We will have something like d minus one dimensional manifold that we are performing the integral over. Right? Any questions so far? This makes sense? Okay. Okay, so now we connect to the quantum picture. Everyone here took quantum field theory? Oh, okay. So, in quantum field theory, we have the partition function. And you also have correlators. And we learned about ward identities. Now, if you've taken QFT, this should look familiar to you. But if not, you can see that it is similar here because on the left hand side you have something like a del mu, del J mu. And on the right hand side here we have a delta function, which means that as long as x and y are not the same, you get 0. So you can see that there's some similarities with the classical case, right? Now, the reason why we have this operator here is because in physical theories, or in quantum field theory, only these correlators are physical. So sometimes, in fact, a lot of times, your operator, if you just take this expectation value, it could very well be 0. So we in quantum field theory, we talk about these correlators. Now, what we want to do is to generalize this to higher forms, we have to use differential geometry. So we are going to generalize everything here in terms of differential geometry. So first, this current becomes a one form. Now, if this is not familiar, we remember that in GR, you've learned differential geometry and that there are things called one forms and vector fields. And since your current has a one index, it should correspond to either a one form or a vector field. So hopefully this makes some sense for why we are doing this. And the Hodge dual of a current is given by this expression. Are you all familiar with hot duo? Okay. No? Oh, okay. I'll elaborate. So this is a way of associating n minus 1 or n minus p forms with p forms. So in this case, we haven't generalized it yet. So we have a 1 form here, and this associates an n minus 1 form. Now I give you some heuristic argument for why we can do this association. We know that your n form in an n-dimensional manifold has rank 1, right? And so this is basically your dx1 all the way to dxn. Now, these indices run from 1 to n. Yeah, 1 to n. And therefore, these 1 forms are n-dimensional, right? And the Hodge duo, you can think of it as, let's say, in an n-1 case, we are removing one of this. And we have a choice of n of them to remove. And so this object, the n-1 form, is also n-dimensional, right? Any questions so far? No? Okay. And so now we can basically redo everything we have here in terms of this differential geometry language. So first of all, we write the continuity equation as the exterior derivative of the Hodge duo of J. And one thing I want to note is that here we're using the Euclidean metric. Yeah, so we have so there's no more minus ones in our metric. And if we expand this, what we'll have is that after some algebra. So we can see that we make connection with what we had originally, right? We could get exactly this expression because we can take for granted that this n forms, these are not zero, right? So it only has this has to be zero. So you can see that we recover our classical mechanics. Now similarly, remember that here we wanted to build a charge operator. So charge operators in the differential geometry language would be basically the integral of this current over some submanifold. Does this make sense? And so we saw just now that we got these word identities, and if we rephrase this, because remember here we're still talking about operators, and therefore we want to talk about word identities instead of this just the classical case, then this expression becomes one thing to know is that because we can integrate n forms over n-dimensional manifolds, the right hand side we have to kind of insert this differential. Okay. How much time do I have left?
5 minutes.
5 minutes.
Yeah. 5 minutes, okay. Okay. So now let's integrate this expression over the manifold. And remember that this was, so this right hand side becomes well, the left hand side then becomes okay. So here we'll call this the link number. And if we return to this picture of this manifold, then we can see that let's say you have a operator placed here, then this manifold does not integrate over this point, and therefore our link number will send this integral to 0, right? Does it make sense? Okay. Well, we can imagine like from here, right? I forgot to emphasize that if these points do not coincide, then the right hand side is 0, right? And so even if you integrate over all j, this statement still holds true. If you integrate over some manifold like this, and your point lies outside, then this is just not at the same space-time point, and the right hand side goes to 0, right? It kind of makes sense. And so I claim that this object, this is a topological meaning, because if we imagine that this manifold and this point are not linked together, then you can deform the manifold and it will still not link together, right? So let's say originally you have this, but let's say I want to do this, and this point is here, right? I can curve this manifold and it still does not touch the point, and therefore the right hand side evaluation will be the same. So this manifold, this charge operator is a topological object. How much more time do I have?
Timing 1 minute time.
1 minute. Oh, okay. I will skip to the punchline. So why is it called generalized symmetries? Previously, I mentioned that this is a constant, and if we can get this a constant is a 0 form that is closed, right? And we can extend this constant to a one-dimensional, a 1 form, and so this becomes now when this is a 1 form, the dimension of this object will reduce by 1. And so Now this will become a J2, and this J2, this current will be a one-dimensional reduced. So, oh, sorry, in this case, the J itself will be one-dimensional higher. So this J2 is and so a higher dimensional charge operator will be this object. And so you're going to draw pictures for this d minus 2, you will have some, instead of being your operator being defined at a point, it will be defined along some line. Yeah, so where C is the line. Okay, thank you.